Hello, now we meet again. Let us continue with the next subtopic in this chapter, 4.2 cofactor and 4.3 inhibitor. Okay, so let's continue 4.2 cofactor. At the end of this subtopic, you should be able to define cofactor, explain the three types and functions of cofactor, metal ion activator, coenzyme, and prosthetic group. What is cofactor? Many enzymes are inactive when isolated in pure state. They need cofactor to activate them. Cofactor is non-protein component required by enzyme in order to function efficiently. Enzymes with a cofactor requirement do not have a properly shaped active site in the absence of the cofactor. Cofactor affect the configurations of the active site to allow the enzyme to combine perfectly with its substrates. Cofactors are often oxidized or reduced during the reaction. But like enzymes, they are not consumed and they return to their original state when the reaction is complete. The inactive enzyme without a cofactor is called an apoenzyme. Cofactors are required by inactive apoenzyme to convert them to active holoenzyme. The term holoenzymes refer to the enzyme's cofactor complex. This figure shows roles of cofactor in enzyme function. The first picture shows when cofactor bind to the enzyme, it changes the conformations of active site, makes the substrate fit well. The second picture shows cofactor participates in temporary bonding between active sites and substrates. The three types of cofactors are metal ion activator, example magnesium ion, coenzyme, example NAD+, prosthetic group, example heme group. Metal ion change the shape of the enzyme to facilitate the formations of an enzyme substrate complex. There are two types of metal ion, one that bind temporarily and loosely, example magnesium ion, and the other one bind tightly, example zinc ion. Coenzyme participate in enzyme catalysis reaction by transporting hydrogen atom and small molecule from one enzyme to another. Coenzyme normally bind loosely to the enzyme. Many coenzymes derive from vitamin, example niacin, riboflavin, vitamin B6 and B12. Example of coenzyme NAD+. Prosthetic group is the non-protein component that bind permanently to the enzyme. Example of prosthetic group is heme. Heme is prosthetic group of enzyme catalase and cytochrome oxidase. 4.3 inhibitor. At the end of the lesson, you should be able to define inhibitor, explain the roles and type of inhibitors, competitive inhibitors versus non-competitive inhibitors, analyze graph related to competitive and non-competitive inhibition. What is inhibitor? Inhibitors are substances that reduce the rate of enzyme catalysis reaction or slow down or stop enzyme control reaction. Usually, inhibitors are specific. They work at low concentration. They block the enzyme, but they do not usually destroy it. Many drugs and poisons are inhibitors of enzyme in the nervous system. There are two types of inhibitor, competitive inhibitor and non-competitive inhibitor. Competitive inhibitor bind loosely to the enzyme, so the competitive inhibition is reversible. Competitive inhibitor have the same shape as the substrate and they compete with the substrate to bind to the active site of the enzyme. When it binds directly to the active site of the enzyme, it blocks a substrate molecules from binding to the enzyme, so reduce the rate of the reaction. Since competitive inhibitor bind loosely to the enzyme, the effect is temporary. Enzyme can be reused again. It causes no permanent damage to the enzyme. Non-competitive inhibitor do not have the same shape as the substrate. They do not compete directly with the substrate to bind to the active site of the enzyme. Non-competitive inhibitor bind to allosteric sites of the enzyme. The binding of non-competitive inhibitor to the allosteric site causes the enzyme active site to change shape. So, substrate can no longer bind to the enzyme. This will decrease the rate of reaction. This figure shows graph related to competitive and non-competitive inhibition. The graph shows rate of reaction with competitive inhibitor is higher than the rate of reaction with non-competitive inhibitor. The effect of competitive inhibitor can be overcome by increasing the concentrations of substrate since they compete with the substrate to bind to the active site. But the effect of non-competitive inhibitor cannot be overcome by increasing the concentrations of substrate since they do not compete with the substrate to bind to the active site.
Let's take a look at this phenomenon called enzyme inhibition using my cute little buddies right here. So here I have an enzyme, here's another enzyme. Let's start here on the left with an example of competitive inhibition. So here is my enzyme. Now this enzyme is actually a complex protein made up of a chain of amino acids folded into a complex three-dimensional structure, but that's okay. It's cute like this. So here's a little enzyme, and normally here's its substrate that it's supposed to bind to, and when it's doing its job, it's nice and happy, and it goes blah, 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 and this gets converted to its products and it leaves, and another one can come along and it can keep on doing that. So what's an inhibitor? Well, an inhibitor is something that's going to prevent this enzyme from doing its job. So in this case, competitive inhibition is where you have some kind of molecule that is very similar in shape to the substrate, and it can actually bind to the same active site. And when it binds to that active site, he's surprised now. Now the normal substrate cannot actually bind, and so you should expect the enzyme reaction to decrease. That's pretty easy to understand. In competitive inhibition, an inhibiting molecule is structurally similar to the substrate, and so it's actually binding directly to the active site and causing this to not work out. In non-competitive inhibition, here's another guy right here. Here's his active site. Here's the regular substrate that's supposed to come in, and when it binds, it's very happy. It goes and then does its job, and it gets converted to its products and leaves, and another one comes in, so on and so forth. Now, in non-competitive inhibition, in this case, you might say, okay, this is a simplified idea here, but this inhibitor doesn't actually fit into this site here. This inhibitor actually binds to another location on the enzyme. That enzyme may not have intended to have another spot there, but it just so happens that whatever this is, this poison, can actually bind in another location. And when it binds to this other location, it actually causes the whole enzyme to change shape. He becomes kind of unhappy and actually affects the actual site of the actual active site where the normal substrate is supposed to bind. So because of this guy binding here at a site that is not the active site, that's very important. This inhibitor in non-competitive inhibition binds to a site that is not the active site, and as a result of binding causes a conformational change to happen to the structure of the active site, and then now the normal substrate cannot actually go in and bind. So that's it. Those are the main differences between competitive and non-competitive inhibition. And I'm going to give you a couple of examples here in a second. So non-competitive inhibition, one more time. An inhibitor binds to an enzyme not on the active site. It causes a conformational change in the active site and therefore a decrease in the activity. So here are two specific examples here. And you should know some examples. You don't have to choose these ones, but here's an enzyme. It's called succinate dehydrogenase, and then take a look at what it's supposed to do. It sounds like it takes succinate and it dehydrogenates it. In other words, it removes hydrogen and turns it into fumarate. So take a look here. There's succinate, compare it to fumarate, and it's actually got 2 less hydrogen atoms. All right, fine. That's what this enzyme is supposed to do. Now, The enzyme is here in the middle. I should bring that guy down. Anyways, okay, here's the enzyme right here. Succinate can bind to the active site, but unfortunately malonate, and this is easy to remember because mal sounds bad, malonate has a structure very similar to succinate, and so malonate can actually bind to this enzyme in the active site, and when this is actually bound, the succinate can't actually bind to the enzyme as it's supposed to, and therefore cannot be converted to fumarate. So this is an example of competitive inhibition where malonate is binding competitively, is competing for the exact same active site. So this over here is an example of competitive inhibition. So a little bit about succinate dehydrogenase. This is important in mitochondria. This is a picture of mitochondria with a little cutout, and there's actually a disease called Lee syndrome, which actually, when you have succinate dehydrogenase not functioning properly, you end up with very low energy levels because mitochondria is important for producing energy. Okay, so that's the example of competitive inhibition. Now for an example of non-competitive inhibition, this one's a little more obscure as an example, but arginine gets converted to something called citrulline and nitric oxide. And this enzyme, nitric oxide synthase, can be non-competitively non-competitively inhibited by opioids. So the opioids can actually bind to the enzyme at a site that is not the active site, cause this enzyme to change shape, and the arginine is not going to be able to bind to the active site like it's supposed to, because this guy has caused its change, the shape of the active site to change. So nitric oxide synthase, okay, remember every enzyme usually ends in ASC. Synthase is inhibited by opioids through something called allosteric inhibition. We're going to see this in more detail later, but for now, allosteric inhibition is synonymous with non-competitive inhibition. And if you must know, nitric oxide synthase is an enzyme that plays many signaling pathway roles. So those are your examples of competitive and non-competitive inhibition. Now let's go one step further and take a look at two graphs here. You're gonna have to study these in detail and then go back and look at some of the examples. Let me try to do this really quickly for you. In competitive inhibition, notice that if I increase the substrate concentration, eventually I can overcome the effect of the inhibitor. So notice that with no inhibitor, everything goes fine. With the inhibitor present, the reaction rate seems a little bit lower, but if I increase the amount of the proper substrate, the concentration of the proper substrate, I can actually end up with the result that's almost like the inhibitor is not really affecting anything. And if you think about that, it's like going back to here and saying if we have a whole bunch of these guys, okay, and these are binding, if I actually have a high enough concentration of these guys here, they can outcompete these guys. Okay, so if I increase this concentration high enough, I can outcompete the actual competitive inhibitor here that's trying to get them to the same site, and so I can overcome its effect by just increasing the substrate concentration. It'll overcome the effects of the inhibitor because they're binding to the same spot. So you can see that here in this graph. Over here though, for non-competitive inhibition, you can see here with no inhibitor everything's fine and dandy, but with the competitor it's lower as expected, but even at very high substrate concentrations I can't seem to overcome the effect as I would in competitive inhibition. So let's illustrate that here really quick. Turn this guy into an infinite cloner, and we have a bunch of these guys as well too. So if I increase the concentration of these guys over here, it doesn't really matter, because as long as one of these guys is bound here, these guys aren't going to be able to come in and fit. So it doesn't matter how many of these actual substrates I produce, they're not competing for the same spot. This can't come fit over here, and these will not come fit over here. So you can't overcome the effect of a non-competitive inhibitor. That's basically what these two graphs are showing. And then here's some writing to help you process that a little bit more as well too. Okay, I think that is a good enough Well, it's good enough for me. Hopefully it's good enough for you to help you understand how inhibitors work with enzymes and the clear difference between competitive and non-competitive inhibition. We're going to take a look at allosteric inhibition, which is a specific example of non-competitive inhibition, a little bit later in the next video. So stay tuned. Thank you very much.